Okay.
So you are seeing this paper of the role of lipid membranes in life's origin.
Uh-huh.
Okay, this is just a paper that I found some weeks ago.
Uh-huh.
It is about lipid membranes in the origins of life. And I just want to show it because it, it, it talks a little about the things that you already said to us about the stability of the membrane in probiotic vesicles. Okay, in this paper, they talk about the origin of life in these places. This is an hydrothermal field. This is like a lake that forms even the volcanoes in the Earth's surface.
Uh-huh.
They think that this is a better place where life could arise, better than hydrothermal vents in the deep of the ocean.
Okay.
And I just want to address that this kind of papers emphasize that the main function of these vesicles of these lipids are to give chemical stability to these probiotic vesicles, and also give some protection against environmental factors like high temperatures or PhD and pH and salinity.
Uh-huh.
And that's important because that we are trying to show with this research is that the UV light and that it is considered as a hazardous component of environment to life is actually very important. The dynamics of the life arise with light in our research, in our proposal. So I want to show you another little paper.
Okay, can I say maybe a little bit of criticism about their approach that it was in these lakes, hydrothermal lakes on the surface of Earth? Well, at the time of the Archean, supposedly there was not very much Earth available, that most of the continents had not yet been formed. So if there were these lakes, there would be very few of them. Even if we had the continents the size of today, I would imagine there would still be very few of these lakes compared, for example, to the whole ocean surface, which is vastly more bigger in size. So would be much more probable from my point of view that life could have started in many different places and maybe came together forming a symbiosis. So that was just a little criticism, you know,
Yeah,
that put with that. Okay.
yeah. I just want to stress that these proposals are thinking only in chemical stability and that kind of things, and they are not thinking about dissipation or light interaction with DNA, with UV light interaction in specific.
Okay, what do you mean exactly by chemical stability?
That these vesicles produce an environment that is
Uh-huh.
helpful to
Helpful to the molecules.
the molecules. Yeah.
Okay.
And the other one I want to show you is this one. This is also a dissipative self-assembly of this kind of structure, but in this case, in this research, they are using as a source of free energy, chemical energy. This self-assembly, they made it with chemical reactions of the kind of Belousov-Jabotinsky, I think.
Okay.
And this is interesting because they are thinking also in dissipation and self-organization through dissipation, but from a different source of energy that the one we are thinking about.
Yeah, so this is through chemical potential, no? Rather through light. Yeah. Okay.
That's interesting because this, I think, and for me, that the things we are doing gives even more opportunity or variability to produce these structures because we are less restrictive. I think, as you say, it's more probably because of the amount of light and the amount of water in Archen, that mechanisms like the one we are proposed are more probable.
Yes, in fact, for example, when you're in the excited state, electronic excited state, which you can do with light, but not with chemical potential. So if you're in the electronic excited state, you have a lot more chemistry available to you. You can do much more. First, because you have the energy, which is higher. And then you also have these other quantum efficiencies for going into things like proton transfer, which you could not get with chemical potential or not easily get with chemical potential. So I think we have an advantage there that in the excited state, we have a lot more chemical reactions which could occur in the electronic excited state.
Yeah, of course. And also want to address that the interaction of light with the DNA with the molecules also allows to explore, actually, as you have said, more and even more mechanisms to this dissipation and structuring. So that's the thing that I'm exploring with my current project.
Okay.
I'm thinking about not only interaction of the light with DNA directly, but I proposed as my research that these kind of structures of vesicles could act as optical cavity to DNA. That means that the light that is incoming to this vesicle could enter in resonance with the vesicle, and that changed the way that the light is interacting with the DNA.
Yes.
So, and that's a phenomenon or an effect that it is not considered in these kind of dissipative systems of chemical dissipation.
Yes.
The optical resonance can only occur when the light is interacting with some cavity. Yeah. So that's another advantage, I think, that we have with respect of this kind of proposed that are based in chemistry mainly.
Okay. So Ivan, you say that we are looking for resonance of the light with the vesicle. So would you say that then would depend on the size of the vesicle and the wavelength?
Yeah, of course.
So, but what exactly, for example, would it mean that if we have a vesicle the size of the wavelength, let's say 260 nanometers, would we assume that we get a resonance if we have a
no, the relation of the wavelength of the light with the size of the cavity depends on wavelength, of course, and in refractive index.
Okay, the refractive index is like measuring two parts. No, one is the absorption.
Yeah, now I'm referring to the real part only.
Okay, so then if we just look at the real part, then we have this wavelength, no? Let's say there's no absorption. We have a wavelength of 260 nanometer light coming in. So if the vesicle is 260 nanometers, or let's say 520 nanometers, or 10,040 nanometers, would we expect to get resonance because it's a multiple of the wavelength? Or how does this relate? Do you know? Have you studied that? How the size of the...
Yeah, it's the cavity length to enter in resonance goes like the refractive index over wavelength, I think.
But what about the size? How does the size of the cavity come into that formula?
Yeah, the cavity size to enter in resonance is proportional to refractive index over the wavelength.
But isn't the refractive index something independent of the size of the cavity?
Yeah, the refractive index depends on the material.
Yeah. And the size, let's say the hole in the center, no, the hueco in the center, that would be another variable distinct, no, from the refractive index. If we assume that the cell wall doesn't change, but only the size changes, then wouldn't that be an independent variable, the size?
Yeah, the size is okay. It's the one size is the size to enter in resonance, and the other is the real size of the cavity. So in this kind of research, people usually design the cavity to have some specific length, but it could treat as a independent variable.
But it's not something so simple as the numerical number of wavelengths which could fit inside the cavity. Integral number like 1, 2, 3 times 260, for example, nanometers. There's no simple relation like that.
I don't understand you.
Okay, I was kind of, because when you talk about resonance, for example, of a string which is vibrating, no, on a guitar, you have, whenever you have an integral number of wavelengths equal to the size of the string, then you get resonance, that tone. So you get, that would be like strong coupling there, no? So I'm trying to see if there's a relation between the wavelength of the light and the physical size of the cavity. Direct relationship, no?
Yeah.
Well, don't worry about it now. Let's think about it, because maybe we can predict what the correct size would be just by the wavelength of the light. If we have a spectrum which is many different wavelengths, then it might be that we have to take only the peak wavelength to find the greatest or the best size of the vesicle for strong absorption.
Mm-hmm. Yeah, the length for resonance also depends on the number of modes. Yeah.
See, maybe, for example, if we, instead of putting our spectrum of light, we put only one wavelength, let's say 260 nanometers, and this then just vary the size of the vesicle or the size of the cavity, and see at which sizes there is maximum resonance, maximum absorption.
Okay, yeah, we can do that.
Because right now you're taking a whole distribution, no, of wavelengths.
Mm-hmm.
Maybe that's making things more complex, because we could get different size, different resonances, but maybe the maximum would be where the intensity is maximum. That would be the wavelength of corresponding to the size of the vesicle that gives greatest absorption. No?
Yeah.
Okay. Okay. See, sorry. Keep going.
Okay, now I'm going to share you an illustration of what I had said. So this is the illustration of my project. So we are thinking that light is entering in the surface, in the ocean surface. And in that surface, we have these prebiotic vesicles that consist in membrane, DNA solution trapped inside of it, and a second membrane, and of course the rest of the ocean. So this is a planar multi-layer optical cavity. We have an initial infinite layer of air, which is the initial media where the light is traveling. We have the lipid membrane, fatty acid membrane, and the DNA solution. This is another layer of DNA solution, another layer of membrane and water. So the idea is the light comes inside the system, and one part is reflected, one part is transmitted in each interface. And finally, we can think that we have the resonance here. That means the light stay inside the cavity and eventually go out. And that is a basic problem of electromagnetism. I have the other picture here. So this is the optics, and this is a periodic layer media. And the one I showed you is not periodic, but is layered, and the physics is almost the same. So here we have the light traveling in X duration, and we have a finite number of layers, each one characterized by a refractive index that could be complex. That means one part measure how the light is deviated when reach an interface, and the other, the imaginary part, measures how much light the layer is absorbing. And so this can be analyzed with magnetism. And where is it? Okay, it can traduce in a problem of linear algebra to computation that depends only in the length of the layers, the angle of incidence of the light, and the polarization of the light. That's the parameters that are needed to run this algorithm. And well, the outcome of this is the absorbance, the reflectance, and the transmittance of this structure. That means the amount of light that it's reflected to the initial media, the amount of light that is absorbed in all the structure, and the amount of light that go out of the whole structure.
Mm-hmm.
So okay, this is my computation of the problem of the prebiotic vesicles. The thing is that we have to calculate the refractive index of the DNA solution. That is possible using Kramer-Kronig relations for absorption spectrum that we have already measured. In my bachelor thesis, we measured some DNA absorption spectrum, so I took them and used them to calculate the real part of the refractive index. Okay, I'm simulating the vesicle membrane with a layer of glycerol. Glycerol is an important composite of the current cell membranes. That's another detail that we have to correct. Try to find a better way to simulate the membrane. But however,
maybe for the membrane would be the hydrocarbon tail, no? So maybe oil. Didn't we try that? Didn't you try that? Oil?
I don't, but I can try it.
Okay.
So here is it. I'm thinking that the membrane is about 5 nanometers of length. We are changing the dimension of the length of the cavity. This is not my last version of my program, but however, we are varying the cavity length from 10 nanometers to 10,000. Here is 4,000, but my latest version is with 10,000.
Mm-hmm.
And I'm using a Python library of, this is the function, TMN is transfer matrix method. That's the name of the algorithm to analyze the optics of this multilayered media. This library was programmed by someone in the MIT, so it's worked well. And it works well. Mm-hmm. So I'm measuring the reflectance, transmittance, and absorbance of the system. So this is the visualization of the absorbance. As we see, we have some cavity lengths that allows to increase absorbance to get a better absorbance. And that's the thing that we are looking for, because this is telling us that the membrane actually allows the light to keep inside the cavity, and then the DNA can absorb even more light. And since we are proposing that DNA is a microstructuring, this is a dissipative microstructure, then we can say that this cavity, the cavity formed by the vesicle, gives the system what it needs to absorb and dissipate even more light.
So the greater the better, no? The greater the size of the cavity, the greater the absorption.
And I did the same for reflectance and transmittance. Okay, so to make a quantitative measure of these graphs, I did the integration of absorbance in this region of 250 nanometers to 280. So I wanna show them. Okay. So I made the integration, and the results are here. This is comparison of the absorbance of the optical cavity I showed you some minutes ago, and compare with the same system but without the two membranes. That's because I'm trying to test the effective impact of the membrane in optics of the system. So I'm thinking in that the main function of the membrane is to allow the DNA solution to stay in some specific spatial region in the surface of Earth. That means that the solution is concentrated in that region. And if I get rid of the membranes, then I'm eliminating the optical cavity effect. So in this second model, that the same cavity but without the membrane, we are taking into account the effect of the DNA solution being concentrated in the surface of the Earth inside a region of the size of a vesicle. And I'm comparing that model with the model with with the membrane. So the first model, that's the one with the membranes, is measuring the optical effect of the membrane. And the second one, that is the model without membrane, it's only measuring the effect of the DNA being concentrated in a vesicle size region of the surface of the ocean.
Okay, and this is integration from 220 to 280, no?
Yeah. Yeah, this is the difference of that integration for both models.
Mm-hmm.
And as we can see, since I'm le estoy restando el modelo sin membrana al modelo inicial. Mm-hmm. So we have this positive difference. Then we can say that actually the membrane, the optical effect of the membrane gives a greater absorption in this region.
Okay. And the greater is the width, the greater the absorption.
Yeah. In my simulation with the cavity width ranging from 10 nanometers to 10,000, this graph reach an stationary state, I think. It stops to increase at about, I think, 6,000 nanometers.
Okay. Six microns.
Yeah. And the interesting thing also is that at the beginning, in very small cavity widths, the difference is negative. So here about 100 nanometers, about 1 micron, this difference becomes positive.
Oh yeah, 0.1 micron.
Yeah.
Okay. So it'd be better not to have the cavity in that case for those small cases, small widths. Okay.
And that's my research. We also are working in this in the reflectance, in the integration of the reflectance at lower wavelengths than 200 nanometers, because we think that maybe the membrane is giving some protection to high energy photons to the system, but when I'm having problems to extend the analysis to that region of lower wavelengths.
Okay, did you see the new absorption graphs that I sent you for the?
Yeah, but I haven't had time to,
okay.
to try something.
Okay. Okay, see, and so there doesn't seem to be a direct relation between the width and the wavelength then. Only maybe at small wavelengths, when the width is less than twice the size of the wavelength, and we get a negative effect with the cavity. But for cavities of larger size, the greater the size, the better, until some limit about 6 microns, no?
Yeah.
Okay, now it's interesting to find the relation between the size of the earliest bacteria or archaea and 6 microns, if they're all greater or smaller than 6 microns. But that's something very difficult to determine, no, from the fossil evidence. But I think there are bacteria, for instance, which have vesicle sizes, which are of the order of 100 microns. No, they're called giant cells. No, but 6 microns is also quite large a cell.
Yeah, but we have positive feedback from the cavity in all this region, not only at 6 microns.
Yeah, okay, but 6 microns would be the
better.
Better, okay. The percent increase in absorption is like 0.2, 20%. Is that 0.2 on the graph on the left?
This is
the difference.
Absolute difference. I have. No, I don't know why I don't have this. This notebook actualized, but in the last I did, I also calculate the percentage difference. I think I sent you by.
Yeah, I thought it was very small. No, it was like 1 or 2%.
Yeah.
So that's the same that you're showing there.
Yeah, it's the same calculation.
Okay, same results.
Yeah.
So about 1 or 2% increase in absorption, no? And that's with the molar extinction coefficient of the vesicle. Did you change that, Ivan, or not had time yet to?
No, I hadn't tried that.
So what did you use for the molar extinction coefficient?
The absorption spectrum.
Of the vesicle?
No, the vesicle I took direct data from internet about reflective index.
Okay. See, but instead of glycerol, try hydrocarbon chain, some large oil, like, well, what would be